This section comes from the lecture outline, Chapter 4, Chemical Stoichiometry, Formulas, Equations, and Reactions. And it will evolve using ideas that revolve around elements, molecules, and reactions. Chemical stoichiometry is the application of mathematics to solving problems in chemistry. The chapter 1 that we went through, it was on measurement, and it used a lot of the math in terms of conversions, dimensional analysis, temperature conversions, and so forth. In this, we will use some of that also, but also using what we call ratio and proportion in greater quantities than we did in the previous chapters. Okay, the first topic in here is the mass and mole concept. In talking about the idea of a mole is a mass number. Keep that in mind. It is a mass. The mole, by definition, is the mass of substance containing 1 Avogadro's number of particles. One Avogadro's number is usually written a capital N with a subscript of 0 attached to it, is defined as 6.02 times 10 to the 23rd units per mole. Yeah, we will use that in some of the problems, which we will illustrate here in a minute. But what I want you to remember, and what makes this all come together real quick, is that 1 mole equals 1 formula weight. In grams. Some people call it 1 gram mole weight. In the context of talking about this, for example, formula weight of water is 16 plus 2 from the periodic table, give you 18. We've been using it to this point in atomic mass units, but drop the AMU, the atomic mass units, and you put grams per mole. So 1 mole of water, 1 mole of water weighs 18 grams and contains 6.02 times 10 to the 23rd molecules of water. If you had formula weight of ammonia, it is 14 plus 3, 17 grams per mole of ammonia. So if I'm holding in my hand 17 grams of ammonia, it will contain 6.02 times 10 to the 23rd molecules of water. And ammonia has 6.02, 17 grams times 10 to the 23rd, make it look like a 3, molecules of ammonia. even the more complex molecules, really not that complex, formula weight of, say, benzene, C6H6 is benzene. Well, it's 78 grams per mole, and C2H6 and is 6.02 times 10 to the 23rd molecules of benzene. Benzene looks like a hexagon ring with a circle in the middle of it. It's something else. Okay, now out of this relationship, you'll have problems that'll ask you, like, how many moles of hydrogen are in 18 grams of water? Well, if 18 grams is 1 mole, and 1 mole contains 602 times molecules, watch me now, molecules, and each molecule has 2 hydrogens. How many molecules of hydrogen, how many atoms, and a hydrogen, not H2, in 1 mole H2O? It'd be 2 times 602 times 10 to the 23rd. So 2 times 6.02 times 10 to the 23rd atoms of hydrogen. There's some logic that evolves out of this definition that you should make specific notations on. How about how many hydrogen atoms are in 1 mole of ammonia, or 17 grams of ammonia? Well, the subscript says 3 moles, okay, of hydrogen. That's 3 times the Avogadro's number over there. Yeah, you will have problems on the exam that will do this. Now, there's some more that goes with this, but right now I'm just working off of 1 mole definition. So the idea is you start applying some cognitive deductions in terms of how you look at these problems, in terms of, well, 1 mole means this, then if then conclusions and so forth. Okay. Now, one of the most important formulas or mathematical calculations you will do in all of chemistry is converting grams to moles and moles back to grams. So next time, long story short, all you want to do is take the grams divided by the formula weight. How many formula weights are there in the given? So the number of moles of substance is always, by definition, given mass in grams simply divided by the formula weight, and that will be in grams per mole. So you can see the invert and multiply off of the units of the formula weight, and grams cancels out and so forth. So the question is, how many formula weights are there in the given gram mass that solicits division process just in that statement, and it's easy to visualize because you already know how to get a formula weight by adding up the atomic weights. And so if you're given a mass number, you just calculate the formula weight and divide into that mass number. Say you're given 8.32 grams of molecular oxygen. How many moles does this contain? So essentially, you are simply converting the grams to moles. So moles, number of moles, O2, you're given 8.32 grams. Well, the formula weight of molecular oxygen is 2 oxygen, each 16, so that's 2 times 16 grams per mole. And so whatever that gives you, 0.26 mole of O2. And it's very important that you are able to do that reflexively. Now what that means is, if I ask you your name, you don't have to think about it, you can just tell me. That's a reflective response. So in converting mass to moles, I'm asking you to learn it in a reflexive format. That is, you simply remember divide by formula weight. You don't think about it, you just do it. Given a mass in grams, divide by formula weight. So it's a very straightforward process, and it's the same from now to you finish chemistry, wherever that'll be. The other side of that is converting moles back to grams, and it's just the opposite of division, is multiplying by formula weight. So converting moles to grams is the other side of this process. Number of grams is always equal to the given moles times formula weight. Of course, that is in grams per mole, and you can see how moles would cancel out very quickly and leave you with grams. And so, given 0.00238 mole H2 gas equals how many grams? And so the formula weight of H2 gas, of course, is 2 grams per mole. That's easy enough, right? And so you're given 0.00238 mole, then the number of grams of H2 gas now is equal to 0.00238 mole H2 gas times 2 grams per mole H2 gas put it all in there. That cancels with that, and you're left with only grams of H2. And just bring it out a little bit for review. And that will be a requirement in some problems, that you be able to convert not just that hydrogen, but any substance given number of moles. You need to go back to grams, because the problems say how many grams are produced in this reaction. Well, you'll solve it in terms of moles and then convert it at the end of the problem in that context. Moles, by definition, is mass in grams divided by formula weight, grams per mole, and grams is moles times formula weight, grams per mole. Like that. And red line, critical that you memorize that and learn to respond to it. And by the time we finish today, hopefully you'll be able to do that. So 1 mole equals 1 formula weight, which equals 1 Avogadro's number, which equals 1 times 6.02 times 10 to the 23rd parts or units. So that shows you the entire conversion factor involved in this. Now we've already covered the idea of what a chemical formula is and how it relates to the mole. Now we need to review what we call percentages and elemental analysis of compounds. And so the percent composition we talked about back in measurement, we'll review it. If you're given copper sulfate, well, it'd be wouldn't be that because copper has 2 and 1. There's your copper sulfate right there. So I need to know the percent copper in there, or percent sulfur and percent oxygen. So when we calculate the percentages, it's the mass of the element divided by the formula weight, and that times 100%. I think you have part over total times 100. All right. Okay, so the formula weight is copper plus sulfur plus 4 oxygens, which is 64 plus 32 plus 4 times 16, and that's grams per 1 mole, right? Or gram formula weight. And so up here, so percent copper would simply be copper mass divided by 160, and that's 64 over 160. Well, you really don't have to put the units down because they're going to cancel anyway, times 100%. And the percent sulfur is then 32 grams per mole divided by 160 grams per mole for the molecule, times 100%, and percent oxygen is 64. Okay, 64 of 160 times 100%. Now, you could add the first two and then subtract it from 100 and get the last one if you wanted to, but just running through that. Now, I'm giving you stuff we've already covered, so it's just in the process making these calculations just to review them. And that was 40%, looks like. That's what I got. 32 divided by 160 times 100. It's 20%. And 4, 5, 6. So that's got to be 40%. 1, 4, 8, 9, 10. Just check that. 64 divided by 160. Yeah, 40%. Always remembering that the sum of the percentages, percent per 100 weights gives you 100%, so you can check your work, okay? And why is that important? Because it's in the sequence of steps that you'll need to follow in determining what we call the empirical formula and molecular formulas. Now, reviewing the types of formulas, the empirical formula is simply the smallest whole number ratio of elements within a molecular compound. You've heard that definition before. Given C2H4 is ethylene, then what's its empirical formula? Well, I can divide that through by 2, and that'll give me CH2. This is the empirical formula. That can't be reduced any further. And this is the molecular formula. And no, I'll leave that. The molecular formula, now just to review that definition, is the actual whole number ratio of elements in molecular compound, in the compound. Now there's a relationship between the molecular weight and the empirical weight, and that's the molecular weight is always equal to a whole number multiple of empirical weight. When you look at this CH2 against the C2H4, you can easily see this one. If you take the 12 and 2, 14, and double that, you will get the mass of the C2H4. And so it's frequently written simply as mole weight to equal N times empirical weight. So that, and we'll use that in the sequence of the formulas we're going to be using in a minute. Okay. So those are some critical definitions that you need to get started in this determination of the empirical formula. So let's take about 10 minutes. Determination of the empirical formula. This is a very straightforward procedure in the calculation process. You'll learn this, and I'll work through some examples. You'll be able to manage anything I can throw at you in regards to this. So the procedure is, actually there are two kinds. It starts with a gram number, but I'm going to give you the generalization. Percent, grams, moles, ratio, reduce, and that gives you your empirical formula. Actually, it gives you the empirical ratio, which you write the empirical formula. Now, I explained this to you. Okay, as indicated, there are two kinds of problems that will come to you, one of two. You might start with grams over here, compound, and a mass of one of the components in a binary compound. For example, out of Ebbing, let's see, this is problem 365 in the 9th edition. Page 119, it goes something like this. An oxide of osmium It's a pale yellow solid and is weighed to be 2.89 grams. And contains 2.16 grams of osmium. Okay. Now, what we need is the percent per hundredweight. Now, this is where the data is given in grams here, and you need to convert to percent. Well, that's percent per hundredweight. So how do you do that? You'll need the mass of oxygen. Well, it's pretty straightforward. So you've got 1.63 grams of oxygen. Now, to convert this to percent per hundredweight is simply part over total. Well, this is your total up here, and these, of course, are the parts of each one. So the percent of osmium will simply be 1.26 grams divided by 2.89 grams, I'll put them in, times 100%. And of course the percent oxygen will either be, oxy will be 100 minus whatever we get up here, or you can put in the 1.63 grams if you want, over 2.89 grams. And this will give you your percentage per hundred. So I got 43.6% per hundredweight for osmium, and oxy gives me 56.40. And you can check these 0.00%. So that just kind of checks your work real quick to make sure you've done it correctly. Now, from this, you move into the sequence that I'm showing you here. This is percent per hundredweight right here. So that's why you would have to convert it. Now, the next example I use when I go through this, the problem will come to you already solved for percent per hundredweight. Let's say the components are so much percent already. What's the empirical formula? And so you just follow the sequence. So let's see how this works. Okay, now what we want to do is follow the prescription that I gave you. Percent per hundredweight is where we are now. And percent to grams to moles to ratio and reducing, you have your empirical formula. Very straightforward. If you listen to me carefully on this, it will be pretty easy. Okay, how do you get this into grams? Well, this is 100% compound right now. So if I have 100 grams, listen to me, just stop writing and listen. If I have 100 grams of this compound, how many grams of osmium am I going to have?
43.
Right there, 43.6. So, and the same way, if I ask the same question about oxy. So to get to grams, this is your percent, and you're going over to grams now. Just drop the percent, put a G on it, because the sum of the two refer to the 100% or 100 gram sample. That's all you're doing. So you go 43.60 grams and 56.40 grams. There's no trick here. 100 gram total weight. Now, the next step is what? Convert to moles. Remember the formula? Divide by what? Come on.
Weight.
Formula weight. Okay, again. What's the formula? Divide by what?
Formula weight.
Okay, everybody got that. So we want to look up the formula weight of osmium. Oh, I'll go back here. Uh, 190.23. Now I'm just going to round it off to 190. So I put a slash here, 190 grams per mole. And oxy I know is 16 grams per mole. Now, we're not dealing with O2 here. It's an embedded element in the compound. So you want your moles of individual element in going through this. So the moles of osmium now, 0.2295 mole of osmium, and oxygen is 3.525, and simply divided by the formula weight of each substance. Now the next step is the ratio. Now this is a two-component compound. So what I suggest to people is put a line, a colon, and a line, because it's two components. On the top, you put your mole values. 0.2295 for the osmium. This is osmium oxide ratio is what we're working toward. And 3.525. Like that. Divide by and reduce. A ratio and then reduce. To reduce, you divide by the smallest of the numbers. What'd I say? Divide by the smallest of the numbers. Well, that's obvious. 0.2295, 0.2295, and that will give you your empirical ratio. And you can write your formula from that. So this is 1 osmium to whatever that works out to be. Okay. The problem gives 2.16. I don't know where I got it out. When I glanced at it, they wrote it down from the wrong problem. Anyway, please correct right here, 2.16 and 789, 78273, and this, of course, will be corrected against the 289. This one's corrected. I apologize. That's corrected, so we'll fix it. So that would be osmium 2.16 and 0.73. And that's 7474. That makes more sense. 25, 26. Now that gives you the hundreds, so we want to now make this conversion. Bring it down here. 74, 74, 25, 26. 74, 74 divided by 190. And 25, 26. Those are corrected. .3934, and 1.5788. Now, we're getting into something that means something. Okay. Let's correct the whole thing. So it's 0.3934 and 1.5788. If you still divide by the smallest number, and so that's 1.5788 divided by 0.3934, and that's correct. Okay, so we have a 1-to-4 empirical ratio, and so the empirical formula is OSO4 in the final analysis. Okay, here's one where the problems worked from the percent per hundredweight. Okay, this says adipic acid used in the manufacture of acrylic plastics has a composition of carbon, hydrogen, and oxygen. And this is problem 3.69 per Ebbing, 9th edition, page 119 also. So we're given carbon, hydrogen, and oxygen in percent per hundredweight already. And so this 50% carbon be sure 5.6% hydrogen by weight and 44.4 oxygen. Now 55.6 and 44.4, so I don't make another mistake like that. So it's going through here from your percentage. We want to go to grams, and so that drop the percentage and put grams on it, and then divide by formula weight to get moles. Carbon, of course, is 12, hydrogen's 1, and oxygen 16. So that quickly converts to moles. Of course, that one is 5.60 grams. For 4.1667 mole, not grams. And I get 2.775. So this is a 3-component formula. So you want the 3 lines like that. Put your moles on top and divide by the smallest of the set. So this is 4.167. We'll just keep it to 0.167, 5.60, and 2.775. So 2.775, 2.775, and this will reduce to your empirical ratio now. So 4.167 is 1.50 to 5.6 divided by 2.775, and that's 2. I'll just leave it at that, and that's 1. Well, what happens here is that one of them is giving us a 1.5. Now, this is one little rule that I always say to this point. If when you get to this point and you come up with a fraction like this, it's going to be one of the following. It'll be 1.25, 1.50, or 1.75, or multiples of those, but the last two digits in there be 0.25, 50, and that comes out of the problem. If that scenario pops up, you have the right to multiply by 2 to create the, in this case, times 2, and your empirical ratio is 3, 4, 2, giving the empirical formula C3H4O2, and there is your formula. So but other problems may pop up and will, that might have one of these others. Now we already see you just automatically go 2, and that goes to a 3. But this one and this one, you need to go to 4. I think that goes to 5, and this one goes to 7. When you multiply those fractions up in terms of 4 times 1.25 goes to 5, and 4 times 1.75 goes to 7. So that is for a scenario where when you get to, after you reduce your ratio, you have a fraction. Now most of them will be whole numbers. You won't have anything that'll show up 1.278 and 1.333. That's not in the problems, because these are theoretical in nature anyway. And so they'll be, now make sure that they fit this rule. Determining the molecular formula. We already given you the relationship between empirical formula weight and molecular weight. That is, the mole weight is always equal to a whole number multiple times the empirical weight. So if you happen to have the empirical weight and the mole weight, you can get the whole number multiple and distribute it through the empirical formula to get the molecular formula. Okay, let's look and see what that's all about. Okay. Here's one. Oxalic acid is a non-toxic substance used by laundries to remove rust stains. The composition is given as follows. And it's carbon, hydrogen, and oxygen. So this one gives us carbon 26.7% by weight. (2.2% of hydrogen, and 71.1% by weight of oxygen. So we go through and determine the empirical formula, get its mass, and then divide that into the molecular mass. So given H2C2O4 is going to be the formula for this, for the molecular formula. I just happen to know what that one is. But the formula weight is given also. I'll just put it like this. I think it's 90 AMUs. So give you a heads up on where it's going. Okay, so to grams is 26.7, 2.2, and 71.1, and you put grams on that if you want, and then divide by 12, 1, and 16, and you get your moles. And it's 2.225 and 2.2, probably 2.225 also. 71.1 divided by 1/6, 4.444. So we have a 3-component molecule, and that's 2.225, 2.2, 4.444, and we want to divide everybody by 2.2. So of course that gives us a 1:1:2 empirical ratio. Therefore, yeah, CHO2 is your empirical formula. So, in determining the empirical turning molecular formula from the empirical formula, we need to calculate the mole weight, the empirical formula weight by adding up the atomic weights. So empirical formula weight is equal to carbon plus hydrogen plus 2 oxys. Of course, that's 12 plus 1 plus 2 times 16. And you can keep it in atomic mass units because they're going to drop out anyway. And so that's 16, 16, 32, 42, 45. 45 atomic mass units or grams per mole, if you want to do that. The mole weight of the compound was given to equal 90 grams per mole. So your whole number multiple is 45 over 90. Well, grams per mole will cancel out, and that gives you 2. So by applying the 2, distributing it through the subscripts of the empirical formula, we have the molecular formula is C2H2O4, and I remember the oxalate is C2O4, and you put the H in the front, you have an acid that neutralizes the 2 hydrogens plus the oxalate, 2 minus. You remember that from hopefully your polyion collection. And so that gives you H subscript 2 C2O4. That's the molecular formula for oxalic acid. So that's the basis of dealing with formulas and converting formulas to molecular formulas and what have you. There are some opportunities online on the website to make calculations on these, and so I would strongly encourage that. So make that correction. Senior moment. Thank you. All right. So we want to talk about how to apply mathematics to a chemical equation. We've been drawing equations, so how do you convert those into numerical values and meanings so we can make hundreds on exams and stuff. Okay, the approach for the most part is really boiled down to ratio and proportion. So I'm going to start with just some simple ratio and proportion things that you already know. And once you see that, then when I explain it, the equation in terms of ratio and proportion, many of you already know this, but if you don't, it is, in my humble opinion, the way to go when working with any of these equations. Okay, what do we mean by ratio and proportion? Okay, if you're given $1, that has 100 pennies. Okay, that's easy enough, right? What if you're given $2? How many pennies do you have? 200? Yes? No? What? Yes. All right. Now that's something you saw immediately in this. So it's 2 times 100, right? Or 200 pennies. Okay? Just to reinforce this idea, let's say you're given a basket of apples. And it contains 50 apples. I'm just making that. How many apples in 12 baskets? How do you get that? One basket has 50, 12 baskets has 12 times 50, right? Everybody agree to that? Everybody see that? Okay, now it has a point here. Or 600 apples. So this is the kind of stuff we're going to use in a chemical equation. And you need to see that, because a chemical equation is defined in terms of its moles, its mole values. And I'm going to explain this entire picture on this to you in that context. What can you calculate from chemical equations? Well, the first thing is moles. Again, the first thing is moles. The coefficients in a chemical equation represent the moles of the substance that coefficient is attached to. For example, if I have 3H2 gas plus N2 gas going to 2NH3 gas, how many moles do I have? Well, that would be 3, 1, and 2 from direct read of the equation. Now, one of the nice things about this is that is a standard equation. How do I know? It is the coefficients in moles are in the smallest whole number ratio. Gives a standard equation. So, as written. And that the conditions, and if you remember, the 0 degrees Celsius at 273 Kelvin and 1 atmosphere, or 760 millimeters of pressure. That's what we call the standard equation right there. Now, that'll be important as we get deeper into this. But what it is in those mole coefficients is what we call a reaction ratio. That is 3 moles of H2 always requires 1 mole of N2 to give 2 moles of ammonia. Now, if I double the hydrogen, that means I must double the amount of nitrogen if I'm going to use all of the hydrogen. If I triple the ammonia, then I'm going to have to triple these two over here. Also, now that's no longer a standard equation because the coefficients are not in whole number ratios, but it's valid. Now I can go through and cut them in half also. One. And it's still a valid equation. Still a reaction will occur. We'll use up 3/2 of a mole of mass number now, 3/2 mole of hydrogen, a 1/2 mole of nitrogen, and a full mole, and we'll produce a full mole of ammonia. Now you can calculate the mass numbers that go with that. we'll do that in a minute. It's called equation. Excuse me. Called equation mass. But the issue of moles, to produce moles, is nothing more than what are you given. You'll always solve these problems in pairs of substances. And their ratios are always referred back to moles, like this. Let's say you're given 0.25 mole of nitrogen gas. Well, how many moles of ammonia gas will be produced? Well, you just did a ratio and proportion for apples and dollars and cents. Well, this is the same thing between the moles of nitrogen here, because all you've got to do is go back to the balance the equation, use the standard equation. That's what you're looking for. Oops, that should be a 3. And that's a 2. So 1 mole from standard we've got 1 mole of N2 will always give us 2 moles of NH3. So what will 0.25 do? It's the same idea. Okay, so that's a quarter of the 1, right? Well, I divide this one by 4. It's 2 over 4, a half. So it's just like the apples and pennies we just looked at. You just pick the 2 that the problem is dealing with and set it up in moles and look at it. Now, if you need the math in this, 0.25 over 1 equals x over 2. Solve for x, and that's 0.50. So you'd have, it's half, right? It'd be half from the 0.25, because you double it against that, because it's 2 to 1 ratio. So we're using a 0.25. Well, this one is twice this. See? It's 2 times. So I need 2 times 0.25 in the problem. I'm working down here. That's why I never did like that. Well, every equation's like that. Let me give you some. Yeah. That's combustion of methane. CH4 and oxygen react to produce CO2 and water. And that's what we learned in equations. What if you're given 12.5 moles of methane? How much CO2 is generated? Well, you look at the coefficients. They're the same. Well, 1 mole will give you 1 mole. So the question mark then becomes 12.5 moles. Well, now the next question is, how much water is produced? Well, this is a 1 to 2. It's twice as much over here. So what do? I need to double the 1 at 12.5 mole. If that's the case. Well, how much oxygen do I need? Well, it's a 1 to 2, so it's a 2 times 12.5 mole. That's separating. And again, that's 25 moles of O2 is going to be used in this thing. And there's gas coming out of the system up there. Say you're given 0.135 mole of magnesium in this problem. Okay, let me balance this thing. I got to put a 2 right there. How many moles of hydrogen you going to be producing? Well, they're the same coefficient, so that would be 0.135 mole of H2 in the yield. Make sense, guys? Any questions? Now, what's the second thing you can calculate out of a chemical equation? And that's grams and mass. Once you find out what the yield is in moles, doing ratio and proportion, times formula weight to get to grams. Now, you may have learned to do grams to moles and all this stuff by dimensional analysis, but I assure you this will stay with you longer. Because if you do the problems in moles, and at the end of the problem, if they want something else in the problem, you convert it. And you already know how to convert moles to grams. You multiply times formula weight, which is 2 grams per mole. 2 to the 5 is 10, 2 to the 3 is 6, 7, and 2 to the 1 is 2, 0.27 gram yield. Hydrogen. We'll take a look at some of the problems and then we'll call it a day. Given the following equation, I got 2C4H10, and that's going to be in a combustion reaction with 13 O2s going to 8 CO2s and 10 H2Os. And it's asking you, well, what's the ratio of butanes, what that is, and oxygen? Well, look at this is C4H10 to O2, and that's a 2 to 13. That's 2 moles to 13 moles. Now I could divide that in half if I had used half as much butane, 1 mole of butane. What would I have? How much of the oxygen would I consume? If I consumed 1 mole over here, how much would I? Well, since that's a 2 to 13, or I split that in half, I got to split that one in half. So that's 13 halves mole used, right? Yes? Everybody see that? Well, all of them are done like that. Every equation. Now, if you're given mass numbers for each of the substances, convert it to moles, and then compare it to the balanced equation. Set up your ratios between the two that the problem's asking for. At the end of the problem, if they want grams, you convert it back. But work the problem in moles first. Because you know how to deal with baskets of apples, why can't you deal with this? Right? They're not going to get any more complicated on the exam than that. You can solve them all if you go to moles and solve the problem. And go down through the oxygen and CO2. Well, we got a 13 and 8. There's a 13 to 8. But if you're given fractional amounts of these, you just compare 13 to 8 is whatever you're given in oxygen to X or something like that. Cross multiply and solve for the unknown. Remember what I said earlier, it's always in pairs. You don't have 3 or 4 of them at one time going on. So when working a ratio problem or one of these stoichiometry problems, and you working through the mole values, you're always simply working in pairs all the time. Solve for the unknown, convert it to whatever they're asking for. And there are different things you convert to. You've got solution concentrations, you've got gas volumes, particle numbers, and we'll get to those in time. I'll let y'all do the other ones. Since they're given the following equation, 2KClO3 goes to 2KCl plus 3O2. We'll play with this a while. How many moles of O2 can be produced by letting 12 moles of KClO3? That's a decomposition. Remember the chlorates? Coach E and COAC, chlorates, bromates, iodates. So they're giving us 12 moles in here. Will produce, and they're asking for moles of O2. Put a question mark over here. Well, 2 goes to 3, 12 goes to what? All right, let me show you some tricks here. Now, this is one thing. Look at the standard equation up here. You're given KClO3, right, down here. And the problem's asking you about O2. Is the coefficient bigger than a 2 or smaller than a 2? It's bigger. Then whatever you calculate better be bigger than 12. Logical? Okay. So by how much? You want this number to go up, right? Isn't that right? You want something here that will make that a bigger number. If you take the coefficients and make a ratio out of those coefficients such that it makes this number bigger. Now what does that mean? That means you have the option of using 2 over 3 or 3 over 2 there. Just take the coefficients and make a ratio times whatever the given is. Which of these two would make a bigger number? Well, obviously, 3 has, and you wouldn't use that one. If it starts out and it asks for smaller numbers, or if the ratio is a smaller number, then you would use a ratio of the coefficients to give a smaller number. Works every time on all equations like this. That's a little trick. Just look and see, well, I'm supposed to get a bigger number here in the standard equation. I better get a bigger number out of this. So 3 halves times 12 is a bigger number than 12. That's the point. I'm trying to show you some tricks out of that. Now, let me get rid of this for a second. So that's 18 moles of O2 produced. How many grams? How do you convert moles to grams? Multiply by formula weight. Yeah. So this is what I'm saying. Work at moles and then times the formula weight. And this is 32 grams per mole. 18 times 32. And that's 576 grams. See how easy chemistry is? Ain't nothing else, huh? Nothing else to do. Through. Go on to the next problem. Convert to moles. Okay? Solve your ratio in moles and then convert it to whatever they're asking for later. The only thing I'm showing you is grams right now. I can show you some others here in a second. Let's see what else we got in our worksheet. Yeah, I got to get through that. Okay. Number 3 in here says given the equation 2KCl2 and 2KCl. Okay, so here's a problem you're given. Na2O goes to plus. Sorry about that. That goes to sodium hydroxide. No, that's the wrong. That's number 4. Well, I'll do number 4. You can do number 3. Okay, because it's just this one. There's 2 NaOH. So let's see what they give us. Okay, how many grams of sodium hydroxide is produced from 1.2 times 10 squared, 120 grams of sodium oxide? So we're given 120 grams, and we'll say that's excess. And so how much of the sodium hydroxide are you going to be? How many grams of, okay, and then you got problem A, and problem B is how many grams to produce 160 grams of sodium hydroxide. All right, let's take a look at that. Okay, what is the rule? Convert to moles. How do you convert to moles? Divide by formula weight. So we're working with sodium oxide, and you go to your periodic chart and you say, well, that's 23. And so I've got, let me rewrite the equation for effect anyway. And so we got 120 grams. So I'm going to divide by 23 grams per mole. Why? Because I want to get in moles, and then compare it to the standard equation, which is what we've just written. And that's 5.217. Right there. Okay. So 1 will give you 2. 5.217 will give you, how do I get that? 2 times 5.217, wouldn't it?
Professor,
All right.
with the 120 grams divided by 23 grams per mole, I believe that should be,
Say again?
the 120 grams divided by 23, the formula weight, I don't believe 23 is correct.
Oh, I picked up sodium right. 23, 16, I mean, 6, 12, 2, 4, 6, 62, right. Sorry. Thank you. Well, it's the same idea. And 1.935, and that's 2 times 1.935 times 2, that's 3.871 mole yield, and that's times 23, 33, 40 grams per mole. And that's, oh yeah, 154.8 gram of sodium hydroxide yield. Well, the second one's the same way, except you're going backwards against this, so you divide that by 40 right there and find out how many moles here, and then you'd cut it in half. Whatever that is will give you the moles over here, and then times whatever that 62. So you're just going backwards, what we just did. Yeah. Everybody good? So far. Thank you. I'll just drop down here, see if I can find a hard one. Number 8 looks like a lot of words in there. Let me try that. Number 8 does. Let's see. I see the equation down here. And that's Fe2O3, good old rust, plus 3 carbons, and that will go to 2 irons and 3 carbon monoxides. Now you start writing out your equation, make sure it's balanced, so you know that's the standard operating procedure anyway. Molten iron and carbon monoxide are produced in a blast furnace by the reaction of iron 3 oxide and coke, pure carbon. If 25 kilograms of pure iron oxide, so we got 25 kilograms given, how many kilograms of iron can be produced? Okay, out of this. Well, it looks like a 1 to 2, right? So whatever moles of Fe2O3 we got, we just got to double it to get over here, and then convert to grams and divide by 1,000, right? So this is kilograms, so that's 25,000 grams, and I need to divide that by the formula weight, and iron's 56, I think. Yeah. So we have 2 times 56 plus 3 times 16, which is 12, that's 10, 11, and 3 times 6 is 48. So 8, 9, 10, 4, 5, 6, 160. So we'll get rid of that. So that's 160 grams per mole. I always do that in the margin of my calculations. So we divide by 160 grams per mole, and so whatever that comes out to be, I don't miss that. 160, 156.25 mole. So now, too long. Okay. So how many moles do we have over here? If this is a 1 to 2, what should I do?
Double.
That's right. So it'd be 2 times 156.25 mole of iron yield. That times 2 equals, that's 312.5 moles. Okay, and that's times 56 grams per mole for iron. And so we have 17,500 grams of iron. I need to get that to moles, divide by what? How do I convert it? Divide by what?
1,000.
Formula weight for iron, right? So once you see what I'm just trying to teach you, now Bob, you're worrying me now. Convert to moles is all we did. I took the kilograms and went to moles, and it was easy. Now you got to go from moles back to grams. You multiply by formula weight. Now the problem asks for kilograms, so we divide by 1,000 grams per kilogram, and that's 17.5 kilogram yield of the iron, right? Everybody good? So this is what I'm trying to tell you. If you can get it to moles, then you can convert to whatever you want at the end of the problem. All right, it is giving us the following equation. 4NH3 plus 5O2 goes to 4NO plus 6H2O, and everybody's, let's see, this is, well, I'm going to call this water gas, even though it's showing a liquid out there. I'm going to call it water vapor. And this is a gas. Now, everybody's gas phase. Well, I guess I could leave it there. Now, in the context of this, we're talking about moles, right? So we can just go right down through here, and this is 4 moles, 5 moles, 4 moles, and 6. I'll leave it at liquid because every time I change something, it's always all about wrong. Anyway, so everybody's good there. Now, all I have to do to get grams, called equation mass, is multiply by formula weight. So this would be 4 times 17 for that one, and this would be 5 times 32 grams for that one. I should put moles over here. This should be 4 times 30 grams, and this would be 6 times 18 grams. And these are called equation masses, and you multiply them out. But you can also calculate out of this particle numbers and gas volumes. particle numbers refer to, well, you can do it two ways. One, you can just look at it, 4 molecules of ammonia react with 5 molecules of oxygen to produce 4 molecules of nitrous oxide and 6 water. That's one way. A second way is relationship to Avogadro's number. This is times whatever that Avogadro's number thing was. So if we really want to know the actual number of molecules in the process, it'd be 4 times Avogadro's number, 5 times Avogadro's number, 4 Avogadro's numbers, and 6 Avogadro's numbers for the respective compounds. And this just depends on the problem that's given. It's still a ratio converted to moles and times Avogadro's number at the end of it. And that gives you the number of molecules in the total process. Now, one that you will use extensively, and when we get to gas laws, and gas law equations, and things of that nature, is what we call molar volumes. What's a molar volume? That's the volume occupied by 1 mole of any gas. Doesn't matter what the gas is. It's any gas in the universe. Hydrogen, 1 molar volume is how much? It's the same volume as 1 molar volume of SO2 or CO2 or any gas that you want to talk about. Right there, it's called a molar volume. Now, the problem is, before I say this, we identify molar volume with a VM symbology. And since this is a coefficient of 4, we're talking about 4 molar volumes of ammonia, 5 molar volumes of oxygen, and so forth. 4 molar volumes there and 6 molar volumes. Well, this one doesn't count because it's a liquid. So liquids do not have gas volumes, neither do solids. So you can ignore those. But you cannot specify a volume until you specify temperature, pressure conditions. Well, in this, the way the equation is written in the smallest whole number ratio, it's a standard equation. And this means that the conditions are 0 degrees Celsius and 1 atmosphere. And you don't have to have a notation on the side that says this is a standard equation. You're just supposed to know if it's in the smallest whole number ratio, it's a standard form. Now, if and only if those conditions apply, can you say 1 molar volume equals a specific volume value? And that happens to be 22.4 liters per mole. No matter what gas you have, under standard conditions, 0 and 1 atmosphere, all gases will occupy 22.4 liters. All of them. So when I want to know the total volume of ammonia in this reaction, 4 molar volumes would be 4 times 22.4 liters if it's at 0 degrees and 1 atmosphere where you're running the reactor. Any other temperature pressure condition, that doesn't apply. That requires another step. But this is where you start. You start with defining the volumes from the standard equation and then convert them to whatever non-standard you would need in a problem. That's another story. That'll come in time. And we have 5 times 22.4 here and 4 times 2.4 here. That doesn't apply because it's a liquid. See what I'm getting at? Now, in every case, all the way through this, I started with moles and then multiplied by formula weight to get a mass, or multiplied by Avogadro's number to get particles, or multiplied by molar volume specifying standard conditions to get a volume. So this is what I'm talking about. Go to moles and then convert at the end to whatever they're asking for. Now, if it's non-standard, you do have another step on the other end that you will learn about when we get to gas laws. But at least, you know, just 22.4 is pretty common. So this is the introduction to how to calculate numbers in equations. What can you calculate from a chemical equation? I'll make the list one more time, and I want you to think about this. From a chemical equation, you can get moles, equation mass, particle numbers, gas volumes, and we'll show you energy numbers eventually, and that's after gas laws. Moles are your coefficients of standard equation. Coefficients times formula weight. Coefficients times Avogadro's number. Coefficients times 22.4 liters. Now that's, of course, all standard equations. Assume. Convert to moles, use the ratio, at the end of the problem. And that's how you do stoichiometry of equations. And what you've learned today is very important, and it'll carry you through the rest of the text. We'll be using it extensively.